All right, so this is 5.1b, and if you remember, in 5.1a, we said that rational expressions that are basically polynomials over polynomials, we use the word p, or the letter p and the letter q to represent those. So p is the top polynomial, q is the bottom polynomial. And in this one, we're going to extend what we know about rational expressions that we did in the first video to rational functions. So remember what we did with functions, f of x, that was the same thing as a y, the up and down. And that is going to equal p of x over q of x. You don't have to understand what that means, just be able to recognize that that's true. So let's just give a little bit of a review on functions as we continue on. If I have f of x, and I say that's equal to x minus 4 over, and this is example 7, x minus 2. And if I ask you to find f of 0, that means that wherever I see an unknown, I'm going to put 0 in its place. So I'm going to put 0 in here and 0 in there. So f of 0 would be what would happen, what would my y value be if I put 0 in for x? Negative 4 over negative 2, which is going to give me a positive 2. So when I put 0 in for x, that's what I get. If I say f of 4, that means I'm going to put 4 in place of x and 4 in place of x there. And when I do that, I get 0 over 2, which is any number. When the numerator is 0 over any number, your answer is going to be 0. If I put f of 2 in, this will be the last one, 2 minus 4 over 2 minus 2 equals negative 2 over 0. Having a 0 in the denominator, I'm not allowed to, so that means we have undefined or the null set. We have no solution there. So let's keep plugging away. The domain of a rational function, top of page 411. If the domain, the x values that we are capable of putting in, is not specified, it is assumed that any number in the whole wide world can be put in for x. Okay? Remember, the domain is the x value, the number that we put in to the function, and the range is the possible numbers that we could get out. So the domain is what numbers can we put in here for x. The domain says that we can, or this problem says we can put any stinking number we want in for x except 2, because 2 makes this undefined. So it's all real numbers except for 2. So that's what we're looking at when we're talking the domain of a rational function. What numbers can we put in here for x that does not make the denominator 0? So that's that little section there. Okay, let's see if I can get this up and out of the way. And we're going to look at example 8. Find the domain for each function. So what they give us is f of x equals x minus 4 over x minus 2. And what they're interested in is finding out what numbers we can put in for x. So we can put in all numbers except 2. Now, rather than write that, we use some symbolism that says the set of x such that x is not equal to 2. So that's how we write that. Okay, the domain for f of x equals x minus 4 over x minus 2 is the set of all x. The set of all x means all the numbers that we could put in there for x such that x cannot be equal to 2. If I had x squared plus 5 over x plus 1, we don't even care what's in the numerator. That doesn't matter. All we care is what numbers work for the denominator. And that would be the set of all x such that x cannot be negative 1, because negative 1 makes that 0. And let's look finally at x over, okay, this is not factored yet, so we can't come up with a domain. So we have to make this difference of 2 squares. Now we can do x such that x cannot be equal to negative 3 would make that a 0. 3 would make that a 0. So there's two numbers that don't work. Yeah, like my little parenthesis there. So that's what we're talking about when we're talking about finding the domain. Find a number, or find the numbers that will work, and find out which ones won't work. So anything that makes that denominator 0 won't work. Okay, so that is section B. Not too terribly difficult. Now we're going to get into difference quotients. Now if you continue this course and you go into college algebra and then off into calculus, this will be some stuff that you're going to be dealing with. So I'm going to go ahead and continue this on this video, and then we will go into a C video later because this is a little bit deep. So I'm going to put the picture on the bottom of page 411 because that's an important picture. And then we're going to also have the picture on page 412 that we're going to put on here. So the book doesn't really explain much about this picture except to say that it is from calculus and it looks complicated. So what we're going to do is try to uncomplicate it a little bit. I'll do my best with it. So we have, let's just look at the blue line here. Let's just look at this. And we just care about the slope. Now, if you remember, slope equals the change in y over the change in x, or y over x. So let's just look at y over x right now. And what that means is that it's this distance from here to here over this distance from here to here. So from this point P to this point Q, the slope is the distance, the numerical y over the numerical x. So if this were a 3 and this were a 6, my slope then would be y, which is 3, over 6, which is x, which reduces to 1/2. That would be my slope. Okay. So in this case, we don't know what those numbers are. They haven't shown us the distance between here and here. But we do know that the whole distance is from here to here, and that's f of a. And we want to know this distance, f of x. So to get this distance, we have to take this whole distance minus this distance, and that will give us that. So let's put a number in here just to make sure you're following. So let's say that the whole distance is 6, and this distance is 4. How would we find out what the distance is between here and here? We would take the whole distance minus this distance, and that would give us our distance of 2 there, correct? Because 2 plus 4 is 6. So this 4 only goes up to here, and we want to know what the whole thing is. So 6 minus 4 is going to give me 2. And that's what they did here. So let's look at this without numbers. And they're saying, so if we took f of x, this whole distance, minus f of a, that would give us the rise. And they're doing the same thing with the run here. They're saying the distance from here to here is x, the distance from here to here is a, and we only care about this distance. So we're going to take the whole distance and we're going to subtract this little bit here, a, and that will end up being our x value, our run. So that's what we're concerned about here, is we're only concerned about this and this, our rise over our run. And notice up here, here's our rise over our run. Okay? So we don't care about this red loopy thing, parabola. We're just going to worry about what we've got here. Okay, so hopefully that makes some sense as far as what this graph means. And we can go on from there. So this right here is called a difference quotient. Okay, that's an important word for calculus, difference quotient, even into college algebra, because you'll be reviewing the same stuff again. So difference quotient. And it will be a rational expression. And let's just do a little bit of practice with it. So we really don't need this right here anymore. I am going to leave it there and just make it smaller. But let's look at example 9. They give us f of x equals 3x minus 5. And they want us to find f of x minus f of a all over x minus a. Okay, so what we're going to find here really is the slope of this equation. So the reason we're doing it this way is because when you get into calculus, these problems get a lot more difficult, and they're not so easy just to find the slope along this way. Okay, so right here, when we put it in slope-intercept form, we look at the slope and we're like, oh, it's 3. Why do I have to follow all of this hard math in order to do it? Later on, you will have to follow the hard math in order to do it. So anyway, example 10 is an example of some harder math. But let's just look at this. We know that the slope is 3 because the number in front, if you remember slope-intercept form, the number in front of the x is always the slope. So let's see if we get 3 when we use this here. Okay, so let's go ahead and get started. So what I do when I figure these out is I find out what f of x is, I find out what f of a is, and then I put them in here and just do the math. So I'm going to find out what the f of x is, and they gave that to us right here. So it's not like I have to do any work here. My f of x, in fact, I do like to write it down, even though it's a second time. And then I'm going to find my f of a. F of a just basically means that I'm going to put a in for x. Okay, so there's those two right there. So that's all I need. So I'm going to rewrite this whole equation. Instead of using the functions, the f of x minus the f of a, I'm going to put 3x minus 5 in for the f of x. And I'm going to put in parentheses, 3a minus 5 in for the f of a, because that's what we have here and here. And I'm going to put that over x minus a. All right, so let's go ahead and combine like terms or take off parentheses. Minus 3a plus 5, because taking this parenthesis off, I have to change that to a plus 5. And that's over x minus a. Whoops, that's not an x. So let's combine like terms. These go away. Negative 5 plus 5 is 0. Leaving me with 3x minus 3a over x minus a. Let's move this up. And I'm going to factor a 3 out. Cancel, cancel, and I'm left with 3. Okay? Not really too difficult to do, but in a lot of work, holy buckets, a lot of work to find that compared to what you're used to doing to finding slope, but again, it makes it a little tougher. And in fact, I'm going to stop this video and go into the third video, and we'll do example number 10.